Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to the online lecture on nonlinear control systems. Today we are going to discuss lecture number 9 of this course. So last lecture we finished on Lyapunov equation and linear system stability, and there we considered a linear system which could be a linear approximation of a nonlinear system x given by x dot equal a x, and x belongs to Rn, which means x is an n cross 1 vector. So we considered a Lyapunov function of the form x transpose px, where p is positive definite matrix, which makes this function as a positive definite function. If you calculate v dot of x using the chain rule as we always do, then with this definition of Lyapunov function, v dot of x turns out to be x transpose times a transpose p plus pa times x, and this common factor a transpose p plus pa, we equate this equal to to minus q, where q is a positive definite matrix, so minus q is a negative definite matrix. So this whole equation is called Lyapunov equation. So this implies that v dot is actually minus x transpose qx, and if we can find p greater than 0 and q greater than 0 that satisfy the Lyapunov equation, then we can conclude that the origin is globally asymptotically stable equilibrium point of the linear system x dot equal a times x. So this is what we this is where we left off in the last lecture, and today we are going to continue discussing this. So there is a theorem. This theorem, you can call it the theorem that leads to perfect Lyapunov function for linear time invariant systems. We all know that there is no perfect Lyapunov function for nonlinear systems, but at least we have a perfect Lyapunov function for linear time invariant systems. So if we are to do Lyapunov analysis on the linear time invariant systems, then we don't have to be have any uncertainties about whether our Lyapunov function will work or not. Well, let's see how this is possible. Given an n cross n matrix A, the following are equivalent. All eigenvalues of A have negative real parts. Number 2, this is the statement 1 is equivalent to statement number 2, which is there exists q greater than 0 such that a transpose p plus pa is equal to minus q has a unique solution which is positive definite matrix p. And so if the Lyapunov equation is solvable with any q, any positive definite q, then that will mean that eigenvalues of A have negative real parts. That will mean that A is a Hurwitz matrix. So you don't have to calculate eigenvalues of A if the equation is solved. If you solve the Lyapunov equation for some q, you are guaranteed that this eigenvalues will have negative real parts. Third, for every q greater than 0, a transpose p plus pa is equal to minus q has a unique solution p greater than 0. Now this third statement is basically making our life a whole lot easier. Why? Because this statement is a little bit weak, that there exists some q greater than 0, which means that we may or may not be able to find that q. This third statement says that if this equation is solvable for some q, then it is also solvable with every single possible positive definite matrix q of size n cross n. So we can choose q to be identity matrix to make this equation an easy one to solve, and once you choose q to be the identity matrix and solve for p, you can if the p turns out to be positive definite, then you can have a surety that A will have all the eigenvalues with negative real parts. So this is basically telling us that matrix A being Hurwitz is equivalent to the Lyapunov equation being solvable with any possible q you can take. So corollary of this theorem is that x dot equal ax is globally asymptotically stable if and only if there exists quadratic Lyapunov function v of x is equal to x transpose px, where p is positive definite, such that v dot is x transpose time a transpose p plus pa times x is a negative definite. So this basically the solvability of Lyapunov equation being relevant to A matrix being Hurwitz, that can be that basically implies that x dot equal ax will be globally asymptotically stable system, because we all know that for linear systems, if the A matrix is Hurwitz, then the natural response of this system would be globally asymptotically stable. That is equivalent to the Lyapunov equation being solvable, or v dot being negative definite. Because obviously if this whole thing is equal to minus q, and where q is positive definite, then minus q will be negative definite, and that will ensure that v dot is negative definite. So that is how Lyapunov equation is related to global asymptotic stability for linear systems. And this v of x is equal to x transpose px, that for any positive definite p, that is a perfect Lyapunov function for LTI systems. All right. The positive definite matrix P is calculated from the Lyapunov equation. So usually we plug in Q is equal to identity matrix and calculate the P, and with this A, if the P positive definite is calculated, then the Lyapunov function is calculated from the solution of the Lyapunov equation. So that is the perfect Lyapunov function for the linear system x dot equal ax. Alright, then there is a next result which is very important for justification of linear control theory, because we all most of the real life systems are nonlinear, and still we apply everyday linear control on nonlinear systems, and the linear control works or behave well because of this result being true. So what is this result? Consider the autonomous system autonomous nonlinear systems. Autonomous means time invariant. Time invariant nonlinear system x dot equal f of x, with f continuously differentiable and f of xe equal to 0, which means xe is the equilibrium point of x dot equal f of x. If the linearization or linear approximation of the system about the equilibrium point has all eigenvalues with negative real parts, then the equilibrium point is asymptotically stable. Then xe is the asymptotically stable equilibrium point of x dot equal f of x in the sense of Lyapunov. So what is this statement saying? So this statement is saying that the stability property of an equilibrium point is invariant under the operation of linearization. So if you linearize a nonlinear system and the resulting linearization or linear approximation turns out to be asymptotically stable, then the original nonlinear system about the point of linearization, which is your equilibrium point, will also be asymptotically stable. As it may look a little bit straightforward, or you might be tempted to take it for granted, but this result is in fact a huge result for justification of linear systems based control theory, because if stability were not if the stability property were not preserved under linearization, then we would have a lot of trouble and difficulties in designing control systems. If the linearization of the system about equilibrium, so this theorem continues. It has three parts. First part says that if the linearization has all the eigenvalues with negative real parts, then the equilibrium point of the original nonlinear system is asymptotically stable in the sense of Lyapunov. Second part says that if the linearization of the system about the equilibrium point has at least one eigenvalue with positive real part, then XE is unstable, which means that the original nonlinear system, the equilibrium point of the original nonlinear system is unstable. And third part is that if all the eigenvalues of linearized system have real parts less than or equal to 0, and at least one eigenvalue has real part equal to 0, then no conclusion can be made. So this part is basically this gives you a paradigm or a domain where the stability property is no longer preserved or translated from nonlinear systems into linear systems. So this can basically this last point can be used to emphasize upon the importance of the other two parts, where you can conclude about the stability of equilibrium point of a nonlinear system from the stability of linear systems or linear approximations. So for linear approximations, we already have learned a quadratic Lyapunov function. For nonlinear systems, we are still struggling to find a perfect Lyapunov function. All right, so let's do some applications of this theorem, or just try to grasp this theorem, the concept of this theorem in a little bit of more clarity. So for example, let us suppose we have x dot equal f of x nonlinear system, and we linearize this system. X dot equal ax is the linear approximation of the nonlinear system, and we know that the linearization is done through the Jacobian. You calculate the Jacobian matrix of the partial f by partial x, and equate x equal to x its equilibrium point value, then you get this matrix. So if the eigenvalues of this matrix are all in the left half plane, open left half plane, then the equilibrium point XE of the original nonlinear system would be asymptotically stable. If the eigenvalues are such that some of them are in the open left half plane, but one of them or maybe more are on the j omega axis, then no conclusion can be made about the stability of this equilibrium point from this linear system. This linear system may have any type of stability, but we cannot conclude anything about the original nonlinear system from the stability property of this linear approximation. Here in this case, the original nonlinear equilibrium point would be unstable because there is at least one eigenvalue on the right side. So remember this, that if in this case as well, if there is an eigenvalue on the right side, then this j omega axis eigenvalues, they don't count, because even if there is one eigenvalue on the right side, the conclusion will be unstable. It will not be no conclusion in that case. No conclusion is only if the eigenvalues are strictly in the left half plane and some of them, or one of them at least, is on the j omega axis. So again, here in this case, all the eigenvalues are on the left half plane and a couple of them on the j omega axis. So no conclusion about the original nonlinear system from the linear approximation. Another example, let us consider this nonlinear system x1 dot equal x2 and x2 dot equals minus x1 cube minus x2 cube, And if you linearize this system partial f by partial x with x equal to 0, this whole system has an equilibrium point at the origin. And when you calculate the Jacobian and evaluate at x equals 0, it turns out to be A equals 0 1 0 0, which is a matrix which is an upper triangular matrix, and its eigenvalues are on its diagonal, which are both equal to 0. So two eigenvalues on the origin, that means it's a double integrator system. And if you have a little bit of a know-how of control systems, then you should know that double integrator system is unstable by nature. So practically, if it was originally a nonlinear system, then if it was originally a double integrator system, rather than being a linear approximation of a nonlinear system, then we would conclude that this double integrator system is unstable. But we know that if the eigenvalues are on the j omega axis and none of them is on the right half plane, then we cannot conclude anything about the stability of the original nonlinear system. We cannot conclude anything about the stability of this equilibrium point from these eigenvalues. So let me show you or try to analyze the stability of this original nonlinear of this equilibrium point using the original nonlinear system dynamics. A linear system with above A matrix would be characterized as unstable due to double pole at j omega axis. But analyzing the original nonlinear system, we can have a Lyapunov function v of x equal x1 to the power 4 divided by 4 plus x2 square by 2, and this is a positive definite radially unbounded Lyapunov function. If we calculate v dot using the chain rule, it turns out to be x1 cube times x2 plus x2 times minus x1 cube minus x2 cube, which is equal to minus x2 raised to the power 4, which is negative semi-definite. So this system is at least stable in the sense of Lyapunov, whereas its linear approximation is unstable. So this is giving you an idea that linear approximation in this case is not a representative of the stability of this equilibrium point at all. But let us further investigate, because this Lyapunov function results in a v dot which is less than or equal to 0. We can still apply LaSalle theorem to investigate about any possibility of global asymptotic stability. So the set S where v dot is uniformly 0, that would be the x1 axis, where x2 is 0 and x1 could be any value. So on this set, if we put v dot equal to 0 implies that x2 is 0. So x2 is equal to 0 implies that in the original nonlinear system x1 dot would be 0, and that would imply that x1 is constant. And also if x2 is 0, then x2 dot is also 0. So in the dynamics, if you put x2 dot equal to 0, then that means that x1 minus x1 cube is equal to 0, which means that x1, which is a constant, we already established that, so x1 is 0. So the only solution of these dynamics, these nonlinear dynamics, that lies on the set S is 0 0. So by LaSalle theorem, the origin of this nonlinear system is globally asymptotically stable equilibrium point. So you see that why the other theorem that we learned on the a couple of slides ago was so important, because in some cases the linear approximation is not even close in determining the stability property of the equilibrium point of original nonlinear system. Here this example is a prime advocate for this case, where the original nonlinear system has equilibrium point that is globally asymptotically stable, provable using LaSalle theorem, and while its linearization leads to an unstable linear system, which is completely opposite of what the original nonlinear system is. So Well, there is a useful formula here that I want to cover at the end of the lecture. Since we are already talking about the linear approximations of nonlinear systems, the linear approximation actually comes from Taylor series, and x dot equal f of x, where f of x is a nonlinear system. This is approximated by a times x plus the remainder in the Taylor theorem, which is Rx. So let's say v of x is equal to x transpose px, and v dot of x is equal to minus x transpose qx. But if we do not ignore the remainder part of the Taylor theorem, then the v dot will have this additional term in it. Now without this term, v dot is negative definite, and we are all happy. But with this term we have a problem. We have a problem only when this term exceeds in magnitude to this term. So if this term exceeds in magnitude, then v dot may not be negative definite, and we may not be able to prove any kind of stability or asymptotic stability. But luckily we can make this term as small as we wish to, because this term depends upon this remainder of the Taylor theorem Rx. This can be made smaller by choosing by appropriate choice of x. So we note that 2 times Rx transpose Px has to be smaller than x transpose Qx for asymptotic stability, and the fact is that the magnitude of Rx can be made smaller by confining by confining the magnitude of x close enough to 0. So this is the mathematically proven fact that as limit the magnitude of x goes to 0, the ratio of Rx over x magnitude is 0. And we can actually show this mathematically as well, that how R of x becomes smaller with the choice of x. So for that we have to look into what exactly R of x is. So we recall the Taylor's theorem that any nonlinear function at a point x equals 0, in this case in general Taylor theorem applies to a nonlinear function at any point x equal to a, but we are interested in x equals 0. So f of 0 plus partial f by partial x at x equal to 0, and multiplied by the higher order derivatives, and there are also higher order terms of x involved. I have missed those in my slides, but you know there is an x square here, and there is a x cube with this term, and so on. So since for our purposes 0 is the equilibrium point of the system, so f of 0 is 0, and this term will go away. And this we all know that partial f by partial x at x equal to 0 is equal to a, and there is an x which I have missed here, so there is a x here. So f of x at x equal to 0 will be a times x plus this remainder which depends upon x square and x cube and so on. So let me just show you that here there is x, and here there is x square, and here there is x cube and so on. So this is now the correct expression, and f of 0 is equal to 0, as I have already pointed out, and partial f by partial x at x equal to 0 is defined to be equal to the A matrix. Now the remainder is this thing. So again here I apologize that I have missed x square term here and x cube term here. So remainder is something that depends upon the higher powers of x. So it's I don't need to explain at this level that if x is close enough to 0, then its higher powers would be even smaller than the value of x. And since x is nearly 0, then x square and x cube etc becomes very small as x approach 0. So that is how you can make r of x to be less than or to be less than the minus x transpose qx by appropriate choice of x. So for approximation we ignore rx in linear approximation, but even if you don't want to ignore rx, or even if you are ignoring rx, you can still calculate the error in your approximation using this formulation, and this can be useful whenever you have to make precise calculations, or you have to make an estimate of what you are giving up when you are approximating a nonlinear system as a linear one. So that's the end of today's lecture. Before I just finish up this video, I would like to go through the whole lecture in a quick succession. So we started by recalling the quadratic Lyapunov function for linear approximations of nonlinear systems, and then we established that if you can solve the Lyapunov equation with any q, then you can conclude that the linear system is globally asymptotically stable. Then we looked at this theorem, which basically assures that the A matrix would be a Hurwitz matrix if you are able to solve the Lyapunov equation with any q, and that leads to the global asymptotic stability characterization of linear approximation of a nonlinear system. Then there is a justification of linear control theory, which basically the theorem that states that if the nonlinear system, if you find the linear approximation of a nonlinear system and that has all the eigenvalues with negative real part, then the equilibrium point of original nonlinear system would also be asymptotically stable. That would be like local result for the original nonlinear equilibrium point. And similarly, if there is at least one eigenvalue with positive real part, then the equilibrium point would be unstable. And if there are all the eigenvalues on the closed left half plane, then we can have no conclusion about the equilibrium point of nonlinear system. Next we looked at some graphical illustrations of the places where eigenvalues could be and the corresponding conclusions about the equilibrium point of original nonlinear system. And continuing in this manner, we looked at an example which was to me the most important example of this lecture, which basically shows you that a linear approximation of a nonlinear system could be completely off in terms of trying to determining the asymptotic stability of the equilibrium point of original nonlinear system. So linear system may not be able to calculate or represent the stability property of the equilibrium point. And then we looked at the approximation part that we generally leave out while approximating nonlinear systems as linear ones. So when you try to approximate f of x as ax, what you ignore is rx. So if you are able to somehow characterize rx, then you may be able to derive a region of attraction, or maybe a region around the equilibrium point where the the results are valid. The results that you obtain from linear approximation are valid on the original nonlinear system. So we noticed that we have to keep 2 times Rx transpose times Px to be smaller than x transpose Qx for asymptotic stability, and the fact is that you can have Rx magnitude to be as small as you like by confining the magnitude of x to be close enough to 0. And we also looked at why this is possible using the Taylor series, and this tells us that as x is close to 0, x square and x cube etc. become very small, so Rx goes closer and closer to 0. So again, let me fix this. So here there is x square, and here there is x cube, and that is now so hopefully this is now free from error. So since there are x square and x cube and higher order terms of x in Rx, so that is why R of x goes to 0 as x goes to 0. And that is all for now, and we'll hopefully continue with lecture number 10 next time. Thank you for watching this video.